Hello everyone, thank you for the opportunity to give this talk on YouTube. I'm Valentin, a PhD student in the University of Geneva and of Lyon, supervised by Anne Verham and Jeremy Blaiseau. I will present my PhD project where I create absorption lines in simulations and use them to infer the escape fraction of ionizing photons. As you know, the escape fraction is a very important quantity to understand ionization. And unfortunately, it's not measurable at redshift higher than 6 because the neutral IgM absorbs all the ionizing photons. So we need to find an indirect way to measure the escape fraction. And the absorption lines of low ionization state like C2 or silicon-2 are a good candidate because they have lines that have a wavelength longer than Lyman alpha. So they are not affected by the H1, the neutral IgM. And they are low ionization state, so they live in the neutral medium like H1. So the picture is that if you have stars covered by neutral gas like here, the ionizing photons cannot escape, and the line photons are also covered, so they cannot escape, and the absorption lines is saturated. Whereas if you have holes in the neutral clouds, there is escape of ionizing photons, and also the line photon can go through the holes, so the absorption lines is less deep, like here. And there have been work done on this, for example, Chisholm 18 and collaborators, where they use local galaxies where they can measure the escape fraction, and they use the silicon absorption lines to try to predict it and then find correlations. So to learn more about that, I will use a simulation to compare the escape fractions and the absorption lines that I find. The simulation I use is a cosmological zoom done with Ramses-RT. And I go down to redshift 3, where I have a stellar mass of 3 billion solar masses, UV magnitude of minus 18.5 approximately. And it's a very high resolution simulation of 10 parsec, so that we resolve the escape of ionizing photons. Of course, there is radiative transfer, and the physics is the same as in the Sphinx simulation by Joachim Rosdahl and collaborators. Now with this galaxy, I will measure the escape fraction in many directions for a few snapshots and create mock absorption lines as seen from the same directions and try to find correlations between the two. We'll begin by presenting the results on the escape fractions. I selected 3 snapshots around redshift 3. And for each of them, I measure the escape fraction in 1,728 directions. For every one of these directions, we measure the escape fraction of every stellar particle of the simulation. Then the global escape fraction is the average of that, weighing by the luminosity of the stellar particles. And what we see is that the average escape fractions, the average of in all the directions, evolves quite quickly. The blue output has an average of 12%, and then in 80 million years, it goes down to 4%. And after additional 80 million years, it's only 1%. And also, there is a lot of variations with directions. For example, the blue output has direction with 0% escape fraction and others with 47. So there is a large diversity. The galaxies are quite inhomogeneous. And so this means that to infer the role of galaxies in the reionization, it's not enough to measure one galaxy. One needs a statistical sample because the escape fraction of one that we measure in one galaxy is not representative of the average escape fraction of this galaxy in 3D. I also tested removing helium and dust to see the difference, and I find that the escape fraction is not very sensitive to helium. The average difference is only of around 0.5%. And the escape fraction is really not sensitive to dust because in all the simulations, the optical depth of H1 is always bigger than the optical depth of dust. So dust has not a major role for the escape fraction in the simulation. Now I want to show you how we create mock absorption lines. I will use a C2 1334 angstrom as an example, but it can be done for any absorption line. First, since it's a metal line and the simulation follows just hydrogen and helium, we have to assume an abundance ratio. So we choose solar abundance ratio, and then the density of carbon in every cell is proportional to the metallicity in the cell, the hydrogen density, and multiplied by a factor to account for the solar abundance ratio. Then to have the density of C2, we need to compute the ionization fractions. For that, we use Chrome, which is a fast code to compute the chemical evolution. So we give it the temperature, density, metallicity, and radiation field in every cell, and it gives the equilibrium ionization fractions. Once we have the density of C2 in the simulation, we can transfer the line using the code RASCAS, which is a new code that is public by Leo Michel Danzac and collaborators. And we use the peeling off algorithm to create mock spectra from a different direction of observations. So I used in this diagram in RASCAS, the photons scatter. And indeed, the absorption lines are resonant lines. So the photons scatter on the gas several times before escaping. And I want to detail that and the effects of fluorescence in the next slide. Here, so I put here a diagram of the levels of the C2 ion concerning the line that I show. So there are 4 levels, and the absorption, normal absorption, is when you have a C2 ion in the ground state absorbing a photon, and it excites it to the 4th level in this diagram. And usually it's a resonant line, so the ion de-excites the same wavelengths back to the ground state and emits the photon resonantly, which can create this scattering that we saw in the previous slide. However, around 15% of the time, the C2 ion de-excites to the fine structure level here, leading to an emission with a slightly longer wavelength. And it's different enough so that the photon escapes the resonance, and it creates an emission like here, which we call the fluorescent emission. And additionally, there are also C2 ions in the galaxy which are populating the fine structure level. So there can be absorption from this fine structure level at 2 different wavelengths. And we take that into account with RASCAS. First, we use PyNeb to compute the percentage of the C2 ion that are populating the fine structure level, and then RASCAS uses that to implement all those transitions. The 6 transitions here are done in RASCAS. So finally, I show you some examples of mock absorption lines we find. So in one snapshot and different direction of observation, we find very different profiles. For example, here there is a deep saturated absorption line. This one has the particularity to have a very large fluorescence. Or we have 2 lines which are quite weak in absorption. And this line is interesting because the fluorescence has a P-Cygni profile here with some absorption and some emission. And this arises only when we take into account the fine structure level of the C2. And this is interesting because in a paper of Anja Scott and collaborators of last year, they find several absorption lines. There is one of them where the fluorescence, several of them where the fluorescence also in P-Cygni profile. And those galaxies are local galaxies. The absorption lines are similar, but if we wanted to compare with the redshift 3 galaxies, it's more complicated. One potential way is to use lensing. And here is an example of the observation of Muse in a lensing cluster, where there is a galaxy at redshift 3, where we can see absorption lines. It's quite new, and it's still difficult to compare with redshift 3 galaxies, but the absorption lines we find seems compatible, and also compatible with local small galaxies like green peas. And now we can ask if the absorption line can be used to trace the escape fraction of ionizing photons. So in this talk, I will focus on the residual flux of the line, which is the property that correlates the best. The residual flux is a ratio of the flux at the bottom of the line over the flux of the continuum, like it is shown here. And here is a plot where we have 3 snapshots, and we plot the escape fractions and the residual flux in many directions of observation. And we see that the points are always on this side, so the residual flux is larger than the escape fraction. So like this, the residual flux cannot be used as an upper limit for the escape fraction. But we argue that there is one thing that has to do to improve this is to apply a dust correction. One way to justify the need of a dust correction by looking at the distribution of the sources of the continuum. So here on the left, I have the UV non-ionizing continuum with dust absorption. And this is to be compared with the sources of ionizing photons here. So you can see it's quite different. And there is up to 60%, depending on the direction of observation, 60% of photons that are emitted here that are emitted in regions when there are no ionizing photons. So this creates discrepancies between the line and the escape fraction and a lot of scatter. Whereas if we use an intrinsic continuum, a non-ionizing continuum, there are still differences due to old stars that still emit at this wavelength, but not in ionizing photons. Now the discrepancy is only of 15%. Another way to look at the need of a dust correction is that we would like to have the escape fraction of the C2 photons. And this is the residual flux, but when we take the ratio of the flux of the line over the intrinsic continuum, this escape fraction is the fraction of C2 photons that escaped compared to the intrinsic. So now we will use a new dust-corrected residual flux, which is this quantity. And thankfully, it is estimable in observations because the intrinsic continuum can be found by fitting the observed continuum to a stellar population, which can give the dust attenuation. And so this quantity we can find it observationally. So now here is the new scatter plot, but with dust-corrected residual flux. We see that now the lines follow more the one-to-one relation, especially for high escape fraction. There is still some scatter, but now the residual flux is a good indicator of the escape fraction. Unfortunately, for lower values here, there are a lot of points that are still in this side, and so for more than 80% of the points here, the residual flux still overestimates the escape fraction. And that is hard to correct, but it's already better than before. I want now to show the main source of scatter here and the difficulty of using absorption lines to predict the escape fraction. It's due to the distribution of C2 and H1 in the galaxy. So I found out that in the simulation, it's not so true that the C2 lives in the same places as H1. You can see here first the bottom image, the ratio of the C2 column density or the H1 column density. There is a huge variation going from 10 to the minus 8 to around 1. And this is due to ionization effects, a little bit from metallicity, but not so much. You can see here, if I take the carbon over hydrogen ratio, there are only 2 order of magnitudes differences. So these variations come mainly from ionization effects. And then this means that in some regions, like in yellow regions, there is a lot of C2. So you can have saturated absorption lines and no escape of ionizing photons. Where in the blue regions, it's the contrary. You have not a lot of C2, so you have no absorption line, and all the ionizing photons are absorbed. So this creates scatter, and depending on the alignment between stars and those regions of gas, you can have points that get scattered, and this varies with time and with the direction of observations. That's the main source of scatter. So that's what I wanted to show. Now I let you with the summary, and I will publish a paper this summer, so go check it if you want to learn more. And thanks a lot for your attention.